All right, let's get right into it. We're going to talk about one of the true workhorses of machine learning, logistic regression. You've seen it in action everywhere, even if you didn't know it. It's the secret to how so many systems make a simple but absolutely critical choice. Yes or no?
I mean, really think about it for a second. Is this email spam? Is that credit card transaction fraudulent? Will a customer actually buy the product? All of these are basic yes or no questions. So how do we get a machine to answer them? Not just guess, but give us a calculated, confident probability. Well, that's exactly the problem we're going to solve today.
Now, if you're thinking, hey, I know how to predict things, why not just draw a straight line through the data with linear regression? That is a great first thought. But it hits a wall, and it hits it hard, especially when our answer can only be a yes or a no.
And here's the problem in a nutshell. A straight line just keeps going forever. So if you push it far enough, your model might predict a negative 10% chance of something happening, or 120% chance, which, makes absolutely no sense. Probabilities have to live between 0 and 1, between 0% and 100%. A straight line just doesn't respect those boundaries.
So what we're really dealing with here is a special kind of problem. You can think of every single outcome as a little coin flip. It's not a fair coin, though. It's weighted, but we don't know how it's weighted. That weight, that probability of success, is what we're trying to figure out. That's the whole challenge right there. So how do we fix this? How do we use the power of a linear model without getting those ridiculous out-of-bounds answers? Well, it turns out there's this beautiful, elegant little mathematical hack that unlocks the entire problem. And here's how it works. It's a three-step journey. We start with our probability, which, as we know, is trapped between 0 and 1. First, we convert that into odds, so the probability of success divided by the probability of failure. That stretches our scale out from 0 to infinity. Getting warmer, but we're still stuck at that 0 boundary. So for the final magic step, we take the natural logarithm of the odds, and boom, that blows the scale wide open all the way from negative infinity to positive infinity. Now, finally, we have a space where a straight line can run free. This whole process, this transformation, has a name. It's called the logit function. This is the heart and soul of logistic regression. It's the translator that takes our tricky, boxed-in probability and converts it into a wide-open, unconstrained value that a linear model can actually work with. Okay, great. So now we've built our model in this kind of weird log odds world. But if I tell you the log odds of something happening is 1.7, what does that even mean? It's useless to a normal person. We have to translate our model's answer back into the language we all understand, good old probability. And to do that, we need the logit's mirror image. Meet the sigmoid function. Just look at that beautiful S-shaped curve. Its job is simple. Take any number our linear model spits out, doesn't matter if it's minus a million or plus a billion, and it perfectly gently squishes it back into a value between 0 and 1. It guarantees we end up with a sensible probability. So let's just make this crystal clear. Think of them as a matched pair. The logit function gets us out of probability world and into log odds world, where we can use our linear model. Then the sigmoid function takes the result and brings us right back out of log odds world and into a probability we can actually use. They're perfect opposites. All right, so we have the mechanics down. We know how to go back and forth. But how does the computer actually find the best possible straight line in that log odds space? How does it learn? The guiding idea here is something called maximum likelihood. And it sounds complicated, but the idea is actually super intuitive. All it's saying is, let's find the settings for our model, the slope and intercept of our line, that make the data we already have look as likely as possible. The algorithm just keeps tweaking the line until it finds the one that best explains what we've already observed. And here's the really cool part. Because of the specific math involved, this problem is guaranteed to have one single perfect answer. You can imagine it like a landscape with just one big, smooth mountain. There are no little hills or valleys for the algorithm to get stuck in. It's guaranteed to find the absolute peak, the one best solution. Now, to find that peak, there are a couple of ways to go. You might have heard of gradient descent. That's like climbing the mountain by taking lots of small, careful steps. But logistic regression usually uses a more powerful method, like Newton-Raphson. Instead of just taking a small step, it calculates the curve of the mountain and makes a huge, intelligent jump right towards the top. As you can see, it's way faster, usually finding the perfect answer in just a few tries. So, the model has run. It's found the perfect fit. We have our numbers. But what do they actually mean? How do we turn all this math back into a real-world useful insight? Well, the most popular way to interpret the results is with something called the odds ratio. All you do is take a coefficient from your model and exponentiate it, raise e to the power of that number. What you get back is this really neat multiplier that tells you how the odds of something happening change. So let's make this real. Let's say we built a model to predict passing an exam. And for every hour someone studies, the odds ratio is 1.5. Okay, so what does that 1.5 actually mean? It's pretty straightforward, actually. An odds ratio of 1.5 means that for every extra hour of studying, the odds of passing the exam are multiplied by 1.5. To put it another way, the odds go up by 50%. It's a clean, simple way to talk about the impact of each variable. But, and this is the final, really important piece of the puzzle, that effect is on the odds, not directly on the probability. And that's a key distinction. A 50% jump in the odds can be a massive change in probability if you're starting near 50-50. But if something is already almost impossible or almost certain, that same 50% jump in odds might barely move the final probability at all. The context really, really matters. Which brings us to this quote, which I think just perfectly summarizes the entire idea. We see that S-shaped curve and we think, wow, that's a complex nonlinear model, but it's not. At its core, logistic regression is just a plain old linear model. The genius isn't in the model itself, but in how we cleverly transform the outcome before we even started. So if this one, simple, elegant transformation can take a basic linear model and give it the power to solve all these complex yes or no problems, it kind of makes you wonder, right? What other simple ideas, what other clever hacks are just sitting there in the data, waiting for us to find them?